והיום אנחנו נדבר על denoising diffusion probabilistic models, או DDPM בקצרה, או סתם diffusion models, ואנחנו נדבר על זה בחתך ספציפי של איך אנחנו משתמשים ב-diffusion models, אלו לגנרות של דוד. אוקיי. Okay, no problem. No problem. Okay, now it's an outline of my lecture. We'll talk about the state of generative AI before and after May 2021. Then I'll talk about what are DDPMs, what are diffusion models. Then we'll talk about some math which behind the diffusion models. It doesn't look so simple, but I'll try to explain it simply. Then we'll talk about some shortcomings of diffusion models and ways we can overcome them. And then, if time allows, I will talk about some buzzwords and some neat tricks that most of the DDPM papers are using. Okay. A couple of words about me. I'm a principal data scientist in social security. What we are doing, we are trying to identify attacks on APIs, and we are trying to tackle it with some machine learning. I'm also founder of deep night learners, which are deep learning papers. We are reviewing deep learning papers in Hebrew. And I'm also co-author of machine and deep learning book in Hebrew. Okay, so let's get started. Okay, I'll start from talking about the generative AI state before 21 May 2021. And what we got? We got some GANs, some very cute GANs, style GANs, cycle GANs, disco GANs, all these GANs, and they have a bunch of variational autoencoders, hierarchical VIE, VQVIE, which is still very popular, and we all know these generative models. And these generative models, also GANs and VIEs as well, are capable of synthesizing some high-quality face images, for example. And there are some late model which is called DAL-E, which is a combination of variational autoencoders and GANs, and this model was capable of drawing such armchairs and having the shape of an avocado. It's cute. These models, DAL-E was also capable of drawing some pentagonal picture frame with quite good quality. But something happened in May 2021. It happened a very interesting thing. So beforehand we have face images, and we have some frames in different colors with very good quality. But then something happened, and now we see, for example, we see our models are capable of drawing of, for example, dolphin and astronaut suit on Saturn in the Earth station style. And for example, we have DAL-E2, which are capable to draw a panda mad scientist mixing sparkling chemicals. And the quality of these images are astonishing. These models are also capable of drawing, of synthesizing, generating these images in a very high resolution. Now they become further. We have imaging from the Google research. We're also capable of drawing excellent quality pictures from longer text. For example, here we have an art gallery displaying Monet paintings. The art gallery is flooded. Robots are going around the art gallery using pedal boards. You can see that the picture just depicts going according to this description, and its quality is just very high. We have many examples. For example, majestic oil painting of Raccoon Queen wearing, many examples. And then they have stable diffusion. And what was uniquely stable diffusion, that was capable to synthesize this picture very fast. The models like DAL-E2, it took about 10 I think 10 seconds, 20 seconds to draw a single image, and Stable Diffusion was capable of doing it in a couple of seconds. And then you have some really crazy stuff, and all these pictures were drawn by generative models of different generative models. But it is not all. We have text to video. We have models which were capable of synthesizing videos from text. Make a video, and some from imaging research, and they have Funaki video. Then we have also text to audio. We have several models which were synthesizing music, audio, and sound from the text description. We also have okay, I don't have internet connection. We have also text to human motion. So we have models which can synthesize a human motion from text description. For example, you can write a text in the style the man is running through the hills, and the model is capable of just synthesizing a video which depicts which goes along this description. So now the question is, what happens? What happened on May 2021? What happened is denoising diffusion probabilistic models, or DDPM. And what happened is this paper, diffusion models beat GANs on image synthesis. And for the best of my knowledge, it was the first paper which claimed that the diffusion models are capable of synthesizing images of better quality than GANs. Okay, I reviewed this paper in Deep Night Learners in Hebrew, so you are invited to read it. Okay, so now we'll talk about modern generative models. What are diffusion? What are the DPMs about? Okay, every generative models we know, it just takes some simple distribution. It can be Gaussian, it can be uniform distribution, or some interval, and then this model is capable of synthesizing a new, much more complex distribution from this simple distribution. For example, we can take a high-dimensional Gaussian distribution and to build from it a picture. The Gaussian distribution is a very simple distribution. We can easily sample from this distribution, and our image data is much more complicated, so it can be easily generated. So the generative model of most types, for example, GANs and variational autoencoders, and the DPMs and the normalized flows, all these models will feed into it some simple distributions, like Gaussian. In most cases, it is Gaussian, and then this model just synthesizes for us a much complex distribution. For example, images, human motion, videos, music, whatnot. So let's talk a bit about DDPM. So like variational autoencoders and GANs and normalized flows, DDPM just generates data from noise. Complicated, it just generates, as I already mentioned, it just generates complicated distribution from a simple distribution like noise. This one. Okay. So now, what is the main principle of diffusion process? The main principle of diffusion process is very simple. For example, we have a data, we have our data set, and we want to train a diffusion model on this data set. So how it can be done? So it can be done in two steps. First, we just destroy the data by adding some small portion of Gaussian noise. It doesn't have to be Gaussian noise. There are some more recent works which are adding not Gaussian noise, but in most cases it is Gaussian noise. And then they just train our model to recover the data by reversing the process model. So they are destroying our data by gradually adding a small portion of noise, and then we just train our model to reverse it. Okay, no, it is not as GANs. In GANs it is done in one step. In the variation autoencoder is done as one step, or here we synthesize our data in multiple steps, in multiple steps. So this process is iterative. Okay, it just look like this. We have some forward diffusion process. The forward diffusion process is just adding of a small portion of noise to the data, and then we train our model to reverse this process. Okay, so but what happens next? What happens next? It is very simple. If we just learn to reverse this process, so for iteration t, we just train our model to reconstruct our iteration time t minus 1. Then we just can feed random noise to diffusion model and generate data, generate new pieces of data. We just do it iteratively. Compared to GANs, to diffusion, to generative models, you know, it is done in an iterative fashion here. Okay, some good pictures of this. So now, then you look at on most of the papers about diffusion models, the math behind it looks very complicated. And you know, sometimes it is really complicated. Diffusion models have interconnection with this so-called score-based model and some stochastic differential equations. But you know, in order to understand what diffusion model is, we don't need to know all this math. Actually, the main principle behind diffusion models are quite simple. And the objective of this lecture is to try to explain you the basic mathematical principles behind the most basic version of diffusion model. Okay? So what is diffusion model? It is a Markov chain of t steps. What is Markov chain of t steps? I already told you that we are destroying our data iteratively by adding a small amount of noise. So at each iteration, we are adding some noise to the content of the previous iteration. Okay? This is the forward process. What forward process does for images, it just turns pixels, you know, each pixel into independent Gaussians. Okay, we have our image. The pixels in this image are usually very related one to each other, and then they are just adding noise, which destroys all these connections between this pixel and turns all these pixels into Gaussian noise. Okay. How this is how it looks like. So we have here our initial data x0, and then we are adding small portions of noise, and then the distribution of the iteration t given iteration t minus 1 is denoted by q. So we just and it is very important that this distribution, it does not depend on xt minus 2, xt minus 3, and in this sense, this process is Markovian process. Okay, and very simple expression. The conditional distribution of xt given xt minus 1, it is just Gaussian distribution. Then the expectation is a square root of 1 minus beta t xt minus 1, and it has some covariance metric. So you see that the forward process is Markovian. So we just take the content of iteration t minus 1 and just adding some amount of Gaussian noise. It is very simple. Okay, so Q, so the distribution of xt given xt minus 1 is just a normal Gaussian distribution. It has expectation of mu t and the variance of sigma t. Okay, here you see you're just adding a small portion of noise to your data x0. And here is mu t, it is just expression for mu t. You can see they are just destroying, we are just adding an amount of noise which depends on the content of the previous iteration. So we're just adding small amount of noise, and it turns our data after big T iteration into independent Gaussian noise. Okay. So, and beta T are parameters. We'll talk about it later. And how we train this diffusion model. Now we're just trying to learn our reversing process by predicting the conditional distribution of xt minus 1, the content of the iteration t minus 1, given t. So doing machine learning, generative AI is based on machine learning. So we just model this reverse process. We just model this distribution by some model. And we just try to train model which mimics this distribution. And this is how it happens. We have a forward process, which we have a forward process which just adds noise to the picture. Then the picture turns to be a pure Gaussian noise, and then we're just training a model to mimic conditional distribution of the previous iteration. And this way we can start from the pure noise. We are doing big T reconstruction step, and we have a new piece of data. There is a very important observation which I want to share with you. Reverse process distribution of the iteration t minus 1 given xt is not Gaussian. It's very important to understand. Because this distribution it depends on your data distribution. For example, this distribution is very different for different data sets. So if you take data set of dog and cat images and the different data set of some images of cars, this distribution gonna be very different. But this distribution, if you condition by x0, this distribution is Gaussian. It is very easy to prove. Very easy. It takes about half a page, but it is very easy. It just uses properties of Gaussian distribution. But it is very important. This distribution is not Gaussian, and this distribution is Gaussian. We'll try now. I will explain how we model this distribution. But it is very important to understand that this distribution is not Gaussian. Okay, so now I ask you, how can we optimize P of xt minus 1 conditioned by xt? Okay, so as I already mentioned, we can do it our well-known machine learning tool. We're just doing log likelihood optimization. Everybody of you knows what is log likelihood optimization. We're just maximizing the log probability of our data set. It's very simple. Just usual stuff. Okay? So, what we know, I already mentioned it, that the forward process is Markovian. So if I condition the distribution of xt given xt minus 1 by xt minus k, it changes nothing. And then how do we approach this problem? We approach this problem with very well-known tools from generative modeling. I think everybody here knows what is variational autoencoder, and it is very simple. It is very similar to find an objective of variational autoencoder. Just here we have many variational autoencoders within one diffusion model. I'll show you now. So they are trying to optimize this distribution. And what is this distribution? It is a distribution of the content of all t iterations given our data. Okay? And the next formula is also very simple. We are just leveraging the fact that our forward process is Markovian. Yeah. Question? Okay. And as we already assumed, we assumed that the forward process is fully Gaussian, and here is the expression. And this expression, we just use Jensen inequality to get it. And this is, I forgot to say, this is our likelihood or data. We're just trying to maximize the log probability of our data set. Okay, so let us start with this formula. So now we are trying to optimize this formula so that we are trying to find a set of parameters theta of our deep learning model, which maximizes this log probability of our data set or log likelihood. Okay. So since 2020, most of the DPMs, based on the idea proposed in this paper, this is not so popular paper, but it contains a set of very important ideas which are been leveraging all the time even in quite recent papers. So how it is done actually? So we just taking our objective, which you have seen 2 slides ago, and we just represent it as a sum of t summons. Okay, the first summon is just a reconstruction term. It is very similar to variation autoencoder. What is this term about? We are just trying to maximize the condition probability of x0 of our piece of data given the content of the first iteration. Okay, so you want to try to reconstruct your data in the best way. So you just here this reconstruction term. It is very similar to variation autoencoders. Now here, these are most important term, the most important terms in this expression. And what is actually written here? What is actually written here? Just we are trying to minimize DKL is Kullback-Leibler divergence. So this KL divergence measures distance between probability measures. So here
it's not a distance. It's not a distance.
It's not a distance because it is not symmetric, yeah, but it is kind of distance. It is not distance. Yeah. You're right. So it is a Kullback-Leibler divergence. So and they are trying to minimize. They are trying to minimize the divergence between this distribution. It is this one is a reverse distribution, a real reverse distribution of our data. We are trying to reconstruct xt minus 1 on our real data given xt and x0, and we want to model it by this distribution. Okay, so we are trying to reconstruct our data in the best possible way, and there is one more term. It doesn't contain any parameter, so we neglect it. We don't use it, and all the theory behind the diffusion process are about optimizing this expression. Why this expression? Because it is just one term. Here you have t minus 1 term, and next we will see how can we optimize this distribution. But you need to understand that this distribution is just what stands behind these distributions. What stands behind this expression? This expression is measures the similarity of our model to the real distribution. This is the real distribution. It is our model, and it is quite similar to what we have in variation autoencoders. Okay. Okay, so let's take a look on LT minus 1. Okay, so let's take a look in our distribution of distribution we have in xt minus 1 given xt and x0. As I already mentioned, this distribution is indeed Gaussian, and we can compute it easily. And here is the expression. It can seem quite complicated. Nothing complicated here. Just games with the base formula and the total probability formula. Nothing complicated here. This is the distribution we have, and this distribution fully follows from our is fully determined by our forward process.
Mike?
Yeah.
Can you give an intuition why this one is normal distribution?
I think I can't give any intuition because it's just, if you I give you an example. For example, you have your image and you're adding Gaussian noise. Okay, you're adding Gaussian noise in many steps. But if you know your initial image and if you know the content of t iteration, you're just adding Gaussian noise. So you know from here you started, and you know the content of the iteration number t. So it is quite natural to assume that the iteration t minus 1, you don't know what is exactly the content, but the distribution. So here is just it is a distribution. I don't know what was the value of the iteration t minus 1, but the distribution of it is Gaussian as I know my initial point and as I know what I'm starting from. Okay. So let's take a look. So this is very standard expression for KL divergence, which is not distance, as already said. And I would like to show this one. Here we have, just want to come back to this slide. Here we have a KL divergence. Now we just want to write it down, the expression of KL divergence. KL divergence is some integral. So now, if the KL divergence is given by, if you want to compute KL divergence between two Gaussian distribution, we have known expression can be computed easily. Okay, so let's see. Let's take a look at this expression. Oh, it's slow. It's clicking. Okay.
The reason that you don't take the symmetric part of the KL is that because you're interested in one side.
Yeah. And now I told you that we're computing KL divergence between two normal distributions. But you can just correct me, but this one is not a normal distribution. And in reality it is not normal distribution. But we love normal distribution, we love Gaussian distribution, it has very nice properties. So we just want to approximate our non-Gaussian distribution by Gaussian distribution. So we train a model to approximate the parameters of Gaussian distribution. And summarizing, we're approximating non-Gaussian distribution in terms of the expectation and variance of Gaussian distribution. Why? Because it is very convenient in a mathematical point of view. And this is the expression, okay? Here the expectation, you saw it in the previous slide, and this is our expectation of the output of our model. The output of our model is just the expectation of the content of the iteration t minus 1. Okay? So this expectation is computed under the ground truth distribution xt given x0. What does it mean? So I already explained that we have a forward process which we add in a small amount of noise to our data. So this distribution is just distribution over our xt. So then they are optimizing our models. We just take our data and averaging all and averaging our objective function over all the given data. And here we are doing very similar stuff. And how do we do it? It's just Monte Carlo. We're just averaging over our whole data. So we have this expression. This is known. This is what we optimize it for, and we're just averaging it over all our data we have. Okay, but now comes the trick. Okay, the earlier papers before this seminal paper, which managed to beat GANs on the generated image quality, most of the papers which come beforehand are just doing that, trying to optimize this expression. And then come this paper, I think several months before this seminal paper, which just proposed to do something different. And what is something different? It's just reparameterization. Now I'm going to show you that with simple reparameterization, we are trying to solve very similar problem, but we are just looking into it from a different angle. Okay? So, and this reparameterization just brought diffusion models to be better than the GANs and variation autoencoders. There are several more optimization, but this one was for me it's the most crucial. Maybe I missed some. Okay. So, in order to understand what is this reparameterization about, we need to recall that xt is just x0, our initial data, with some gradually added Gaussian noise. This is an essence of our forward process. Okay, here they are just adding noise, and they get the content of the iteration t. And this distribution can be computed. You know, it's just some math. So they are adding many portion of Gaussian noise, and you know the Gaussian distribution has a very good property. When you add two Gaussian variables, you get another Gaussian variables, which expectation and the variance can be easily computed. And this is the expression, okay? So, and why do we need this expression? Okay, so we have expression from x0 through xt, and now we can use this expression in order to transform our expression from ut, which is an expectation of xt minus 1 given xt and x0 in this way. Okay, and here epsilon is a standard Gaussian noise. And why is it good, you ask?
Right.
So first of all, you can see that x0 is not there, and so, and now we are not going to 5 minutes. 10 minutes. Okay. Okay. So and now we are not going to train our model to approximate the content of iteration t minus 1. We are going to train our model to approximate the added noise. And why is it good actually? Why? What is the intuition? Why did it bring us these great results? And the reason is we are just our neural nets are just good in approximated standard Gaussian. We like it. Standard Gaussians are very good. They have very good properties. They are near zero, they are asymmetric. So we are just good in it. So, and now the final steps. We have this expression. Okay, this is just the expression we have in the previous slide. And now this is the final DDPM objective. So we are just LT minus 1. It is written as some coefficient. This is not so important. And here it is just our real noise. And here it is just our noise which we are approximating with our neural net. Okay, and this is our objective. So we took this objective, the variational objective from the previous slide, and then we transformed it in this form. And now we have a sum of these terms. Okay, this is xt, but now it's going to get simpler. This seminal paper of 2021, we don't want to use it. It looks ugly, so let's just drop it. And they really dropped it. And now this is the final objective. Okay, so here it is a final objective. This way, the most basic diffusion models of middle 2021 works. We're just training our neural net to approximate our added noise. Okay, now I want to elaborate a bit about, here we have an expectation of x0 over t and over epsilon. And what all this averaging is. This averaging is, first of all, the averaging of our data samples, of our noise data samples. Then the average over iteration t, and the averaging over random noise samples. So we're adding noise, and we are trying to estimate a noise which was added at each iteration t. Okay, so and this is a very simple algorithm. And this way, we just train our DDPM. We have our data. We are just using normal distribution to get our iteration T. Then we sample Gaussian noise. Then we create in one step. We are not going to do many steps, because now we know how to create xt straightforward from x0. We don't need to create x1, x2, x3. We can do it in one step. And then we are just doing gradient descent step on this expression.
And you necessarily converge what you want to converge?
Not always, but again, but it is.
Again, you don't converge necessarily.
It does not always converge, and you need to work out this coefficient in order to cause convergence, and that's why it is very important how to choose these coefficients. This coefficient beta t, and I will talk about. I have 5 minutes, so I will talk about it. And this is a generating process. So we are just generating noise. Then we generate generate z. Let's drop it. Then we generate a portion of noise for the iteration t. Then we generate. Let's look at 6. Then we generate the content of our iteration t minus 1. In this way, it just follows from the formulas from the previous slides, and then you generate this content from this expectation. Here you have sigma t. So I answered to Uri that it not always converges. So there are two. There are two parameters which are crucial for convergence and the interconnection between them, which is sigma t, so which is a variance with which you generate your data, and the alpha t, which controls the variance of the forward process. Just once. Okay. So as I already told, if you just try to build your own diffusion process without learning how to build beta t's and sigma t's, it won't converge. So it is very important to understand. We have two sequences of parameters, sigma t and beta t. And beta t, it is very important, it controls variance of the forward process, and the sigma t controls the variance of the reverse process. And all this, and the convergence of the diffusion model of this process, and also the quality of the picture you generate in this process depends on many factors, but among them, this one very important. So I don't have too much time, so I want to show you. There are much research now how to choose these parameters. Okay, but I want to skip this. I want to show you. Okay, so the last thing I want to show you. I have a couple of more slides, but I don't have time. And I want to just show you how we can look at diffusion the diffusion models from a different angle. Notice this angle. 10 years ago, I think I have been working for several years in signal processing. So the different angle is a Fourier transform. I like it, and so let us see the diffusion model through a prism of Fourier transform. Okay, so now we have this very cute image, and here we have a Fourier spectrum of this image. Why we have mostly low frequencies? Anybody has an answer?
Low frequency because the high frequency is noise. It
is much simpler. It is much simpler and less mathy. So we have very strong local dependencies in our image. So this pixel is very dependent on this pixel, but it's not so dependent on this pixel. So we have edges, but we don't have too much edges. So we have mostly low frequencies when we put our image through Fourier transform, we get mostly low frequencies. Okay? Now, so let us see if we do Fourier transform for Gaussian, then we get the Gaussian. Okay, now let's see what it is done with the diffusion process. Here we have our generative process. Here it is the content of the iteration t, and now because the Fourier transform is additive, we have this representation. And now let us see what happens in the beginning and in the end of this diffusion process in the terms of Fourier spectrum. In the beginning, this alpha t bar is very close to 1. So we have a very low frequencies, a very small representation of spectrum here. And now then we add it to the representation of pictures. What we are doing, we are just destroying an edges. So the content of the image is preserved, but what we are doing, we just manage to destroy some fine, delicate details. But we can easily understand what was the content of this picture. And then you are going and then you continue your forward process. You're adding more and more noise, and then you just wipe it off all your pictures. So all your details, all your content. So you start from destroying high frequencies, and then you are destroying the low frequencies. So you're destroying the content. And last slide. So if you look at the diffusion models from the through the spectrum of through the prism of Fourier transform, so what we just see. What did we see? We see that the early forward process iteration, they destroy fine image details, but the content is preserved. And then we continue our forward process, we're adding more and more edges, and then we destroy an image totally. In the reverse process, we start the first iteration of our reverse process. We start from reconstructing the coarse details, the content of the image, and then on the later iterations, we just reconstruct fine details of the image. So in other words, we're just deblurring the image. We're just deblurring the image. So I think this this view is very interesting. I think I saw it in some lecture, but it doesn't appear in many places. And I have many more slides, but I stop here. If you have some questions, please ask.
I think you can continue for another 5 minutes because.
So I can continue.
Yeah,
I can continue.
another
Okay,
5
okay,
minutes.
okay.
Because it should be 7:30.
Okay.
The lecture is until 7:30.
So-
we're now 7:30.
so
Can I have
So
can I
it's
have a
important.
question? If we have 5 more minutes. Do you think they went, when they got this good solution, do you think they went from the theory, or do you think they saw that a few years before there were some interesting papers with super resolution that they actually predicted the residuals and just said, let's try this?
I think it is more in the style of let's try it, but you know, do you know what is progressive GAN?
Yeah.
Progressive GAN is a predecessor of style GAN, which is and what is the main idea of ProGAN? The main idea of ProGAN is to start generating of image of size 8 on 8, and then you are just progressively increase you train your network to progressively learn your image. So here they took very similar approach. But by the way, the first paper about diffusion process was written. I don't remember who was the author, but it was written in 2015. 2015. Yeah, Yasha Soltykson. Very famous person, and I think somehow they took some inspiration from this paper of progressive GAN because you know how kids learn drawing. They start from drawing some basic stuff, some edges, and then they learn to add some delicate details. And the diffusion process is working very similar. So you are just destroying your image, and then you are trying to reconstruct it from the content to the fine details. You know, experienced artists don't draw this way, but this is a way of learning.
You have videos in Photoshop that they actually start with blurs and they add the fine details little by little.
Okay.
Layering.
Okay. So I want just to tell a couple of words about flaws, several flaws of diffusion models and how we can overcome it. So you can guess the synthesizing of imaging with the diffusion models is time consuming and expensive. Why is time consuming expensive? Because we are not synthesizing these images in one iteration. So we are doing it iteratively, and I think this paper of 2021 it had 4,000 iterations. Now imagine you need to do 4,000 iterations to synthesize a single image. So this is very slow and expensive. But there are some ways. So there are many papers how we can reduce the reverse iterations. Okay, there are these papers try to predict step t minus, for example, step t minus 4 from t, or step t minus 10 from t. And there is one quite famous paper. They just try to destroy the Markovian assumption of the forward process. Okay, we can destroy a Markovian assumption of the forward process, so we can do some forward process which is not Markovian. We can add noise which is dependent not just on xt minus 1 but only on x0, and somehow it enabled to reduce this iteration by a factor of 10, I think. And the second way, and which is what is stable diffusion about, so all this stuff, all this reverse process and forward process, it was done in an image space. So yeah, it was some upsampling. So they just first train a model to synthesize an image of size 64 on 64, and then they do two upsamples to the size 256, and then they upsample it by a factor of 4. But still, they are doing it in the pixel space, and it is expensive. And then the question is, why don't we do it in the latent space? So we can embed our image into some latent space and do all these steps in the latent space. It is much faster because we can make our latent state quite small. And the stable diffusion, which is very favorable, very famous buzzword. I think before ChatGPT it was the famous word in the generative AI. But stable diffusion, we just don't need. It did one, and it did two, and it has some neat tricks as the classifier guidance and the unit representation, which I don't have time to talk about. So if you want to learn about it, you can ask me. And now I need to stop. Thank you.
Mike, I have a question.
Okay.
How now that you want to generate a new example,
Okay.
how do you condition on what you want to generate?
So you are talking about conditional generation. So you want to condition your image on some text. So for this purpose, you have language model. So you embed your text with some language model, and then one of the inputs to your diffusion model, which you train, is this embedding. So you have some very big language model. You embed your text, and it is one of the inputs. Now your inputs were noise and iteration, and now you have an additional input, which is embedding of your text. And all this I have some slides about it. I want to show you. It's all this famous word here. Just like that. An old painting of a corgi wearing corgi is very. It's a very popular dog type. Anyone who wants to draw images with corgi, I don't know why. So you have a text encoder, okay? and then you just embed your text in some vector. Then you take this embedding, and they use a clip, which is very popular model for text embeddings and for image embeddings simultaneously. And then you just put this embedding into another model, which turns this embedding into an image embedding you want to generate, and then you are doing all your diffusion magic, but conditioned on this image embedding. Okay, and there are additional models which don't have this middle step. They are just trained, for example, imagine don't have this model. It has a frozen text encoder, and from a frozen text encoder they are just generating an images. They are doing it in 2 upsampling step, but they don't have a model which purpose is to train an image embedding from text embedding. So it is not a mandatory step. But and one more difference, they use frozen text encoder, and the DAL-E2 they train it. So there are many neat tricks how can you do it, but the essence is very similar, and very similar you can also generate an audio, music, a video. The approaches are very similar. You embed your text, and then you train your conditional diffusion model. So you just try to build a model which estimates, which tries to predict the noise you added, but given your embedding, number of iteration, and the content of the iteration number t. Yeah, question?
Yeah. You're saying training. How much time do you train? How much computing power you throw at training? Give us some examples. It doesn't have to be exact, but.
Actually, I don't remember. I know that it is quite expensive. I don't think you can train it on your laptop, even if you have a very powerful laptop. I don't think you can do it. Although there is some model I saw a week or 2 weeks ago, they claim that you can fine-tune your diffusion model on your laptop, but fully training of diffusion models, I think it is. I don't want to tell you to just imaginable number. I don't know. I don't remember. But it's very expensive.
But
I can give you an example if you want. I worked for a little while in Google, so we trained this Imagine model.
Okay.
Trained a variant of this Imagine model. It only took 2 days, but we used 128 GPUs.
GPUs or TPUs?
TPUs.
Ah, okay. So it is very expensive.
Yeah.
You don't have TPU on your laptop.
And the data you feed it has to have all sorts of dogs and all sorts of like ads and whatever.
I think you just train it on the data set, which is very similar to Clip, right? Which you scraped from the internet pictures with tags or captions, and this is the same or very similar data set as you used in Clip embeddings.
So you have the image and the text associated.
Yeah.
Okay.
Yeah.
Thank you.
Okay, thank you very much, guys.